first thing you have to do in any situation like this is to read the question. Any teacher you've ever come across will tell you that, but it's amazing how many candidates rush straight in without looking at what is asked. First of all, we're asked to solve a differential equation. There we are. Solve the differential equation. And there's the differential equation, and it looks like it's separable variables. We have to solve it for x greater than 0, and you need to ask yourself, why should x be greater than 0? I'll come back to that in a minute. We're then given our boundary conditions so we can work out the arbitrary constants of integration, and then we're asked to write the answer in the form t squared equals f of x. It's amazing how many candidates finish a question and are so keen to get on to the next one, they leave it in the format that they finished it with and don't leave it in the required format, a mark thrown away uselessly. Okay, so let's look at for x greater than 0. Why should x be greater than 0? Well, it all comes from this, log x. Consider the graph of log x. Y is the natural logarithm of x. Natural logarithm of 1 is 0. Logarithm of any number to any base is 0. But you'll see that it's only defined for positive x. And that is why we required that condition there. Now we can set about trying to solve this differential equation, and I want to look first of all at that expression, dt by dx. We have learnt from the very beginning of calculus that dt by dx is not a fraction. It might look like a fraction, it might taste like a fraction, it might even smell like a fraction, but it's not a fraction. But the good bit is that it behaves like a fraction. Think of how you do the chain rule in differentiation, for example. So we can treat it as a fraction for the purpose of solving this differential equation. And what we're trying to do is to arrange to have all the x's on one side of the equation and all the t's on the other. And we can achieve this by a very simple piece of cross multiplying. Now that expression as it stands is incorrect, it's mathematically meaningless until we add an integral sign to both sides of the equation. And that is now a correct deduction from this original differential equation. And what we have ended up with now are basically two integrals. The first of which is fairly straightforward, and the second of which will require a little bit more careful. We're now faced with this second integral, and the problem is that log x cannot be integrated, but it can be differentiated, and there is a method of integration which involves differentiation, and that is integration by parts. Integration by parts comes from the product rule for differentiation, and in order to do it, I think I'm going to write this in a slightly different form. I'm going to write it as log x 1 over x squared dx, which will make it clearer which the u is and which the v is. This is going to be my u, and that is my dv. So we get uv, log x is u. Now v is the integral of this expression. The integral of 1 over x squared is minus 1 over x. It's one of those that really ought to roll off the tongue because it occurs so frequently. Minus the integral of v, which is the minus 1 over x we've just got, du. That's u. Du, the derivative of log x. Again, one of those that really ought to roll off the tongue. And it is 1 over x. And we'll tidy this up slightly as we go along. Minus 1 over x log x plus the integral of 1 over x squared dx. Now, the integral of 1 over x squared we've actually just done here. So, and again, as I said, it should be one of those that just rolls off the tongue. So, minus 1 over x log x minus 1 over x plus a constant of integration. I've already used c, so we'll have k this time, and we'll finally tidy that answer up to minus 1 over x into log x plus 1 plus k. Going back to the original separable variables equation, we have now solved that integral by parts, and there it is up there. Now, we don't really need two constants of integration, c and k, so we can get rid of one of them. And now we can put in the given boundary conditions. When t equals 2, x is 1. So a half of 2 squared plus c is minus 1 into 1 plus log 1. But log 1 is 0. Half of 2 squared, half of 4 is 2, plus c is minus 1 times 1. In other words, minus 1. And c is minus 3. Substituting this back into the original equation here, we get a half t squared minus 3 is minus 1 over x into 1 plus log x. So a half t squared is 3 minus 1 over x into 1 plus log x. And t squared is 6 into minus 2 over x into 1 plus log x. Remember that we were told to write our answer in the form t squared equals f of x. If we left it there and rushed on to the next question, we'd lose the final mark, which is rather a pity. Okay, so my final answer I'm rather proud of. So I'm going to underline it. In fact, I'm going to do more than that. I'm going to surround it with a little red box. Looking now at the mark scheme for this question, we begin with the first part, the separation of variables. There is M1 there for getting the separation correct, and A1 for that first integral, the integral of t dt. And now looking at the integration by parts, there is a method mark for attempting to integrate by parts. So you would pick up a method mark at about this point here, I think. There's a first accuracy mark is for two things. It is for getting the integral of 1 over x squared as minus 1 over x, and for getting the derivative of log x as 1 over x. And so the accuracy mark comes for those two parts there and there. And the final accuracy mark comes for the answer minus 1 over x into log x plus 1. It doesn't matter if you miss a constant off at that point. So there are 3 marks altogether for that section, the integration by parts. Now moving on to the final part of the question, the substitution of t is 2 when x is 1. You would pick up a method mark at this point for correctly substituting t as 2 and x as 1. But you wouldn't pick up anything at all for getting c as minus 3. The final accuracy mark comes at the very end when you get it in that form, as you were required, if you remember in the question, t squared equals f of x. So the final accuracy mark is for this final answer. And if you, as I said before, are too quick to get on to the next question and leave it as the previous line, like that, for instance, I'm afraid you would lose that final accuracy mark. Well, I hope you found this video useful, and if you did as I suggested and tried the question first, I do hope that you managed to pick up all 7 marks. If you didn't score 7, then I hope that you've learnt something useful en route. If you like this video, please subscribe to my channel and tick like. Now on my website, there are many more examples of A-level questions explained in far greater detail than I was able to do in this short video. This is my second video, but I'm planning to add more soon. So see you again. Goodbye.